Well, good day, everyone, and thank you for joining us today. My name is Dave Mercer, and I will be the moderator for our presentation. I'm a member of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, that is, our people, are at the core of our success. Today's webinar is titled Emission-Driven Cleanroom Ventilation Optimization. The presentation focuses on the optimization of cleanroom ventilation systems, with particular emphasis on design strategies, with an approach that enables adjustment of ventilation parameters, resulting in improved energy efficiency and reduced operational costs. The second part of the presentation will explore modern automation systems that support environmental control in clean rooms. It will cover their functionalities, ventilation control modes, and solutions for occupancy monitoring and personnel flow management. The presentation aims to demonstrate how emission-based design and intelligent control can create optimized, energy-efficient, and safe working environments. Now, to set the stage for our safety topic, we have Paul Wood. Paul, now over to you.
Thank you, Dave. Today's safety topic is that safety begins at the design phase of a project. Intentional design minimizes human error for the life of the facility, enhances serviceability while limiting undue risk, and creating a foundation of risk awareness and operational excellence for all involved. HVAC, or heating, ventilation, and air conditioning, is a major contributor to how safe a facility can be operated, not just by airborne contamination control, but also through redundancy of critical systems, emissions monitoring, thoughtful sensor placement, and safe change filtration arrangements for hazardous environments all contribute to the safe operation of a facility. The engineer's goal, among many in design, is to identify potential hazards and risks to make considerate choices to ensure the design is safe, code compliant, and operable. Hence, all engineers play a strategic role in shaping a safe environment. So please take a moment at your next design choice and acknowledge the potential impact your decision may have. It may prevent countless incidents for those yet to ever see the arrangement you are considering. And now I turn it over to our resident HVAC SME, Roman Gubala, to guide us through the concepts and application of intentional HVAC design for clean rooms.
Good morning, good afternoon, welcome everyone. I would like to sincerely thank Paul for introducing such an excellent safety topic. I believe it is extremely valuable because it shows that safety begins at the design stage. This is when decisions are made that often determine the safety of the entire facility and the well-being of many people. And now let's move on to today's agenda. I will start with a brief explanation of what cleanrooms are and why proper ventilation is so important in these spaces. Next, I will focus on emission-based modeling approach, where I will explain how to identify source of contamination, calculate ventilation airflow rates, and review the key mechanical components of a well-designed ventilation system. After that, I will hand over to Damian, who will cover topics related to the control system. We will conclude our presentation with a case study that demonstrates the strengths and limitation of presented methodology. Let's start with the basics. What exactly is a clean room? This is a key question because a clean room is a classified space that must meet specific standards and requirements for air cleanliness inside the room. The two main standards that define these requirements are ISO 14644 and Annex 1 to European Good Manufacturing Practice (GMP) standard. Cleanrooms are environments with extremely low levels of contaminants. They are used to ensure the required quality of manufactured products of the high precision of research activities. Contamination control in cleanrooms is achieved through proper air filtration, regulation of environmental conditions, strict operational procedures, correct execution and finishing of surface. As mentioned earlier, effective contamination control in cleanrooms is built on four key pillars: proper air filtration, control of environmental conditions, correct room construction, gowning, and operator procedures. The first element is the air filtration system. Air supplied to the cleanrooms pass through the special HEPA and ULPA filter. High efficiency particulate air HEPA filters remove at least 99.97% of particles with a diameters of 0.3 microns, while ultra-low penetration air ULPA filters achieve even higher efficiency, 99.995% of particles as small as 0.12 microns. This ensures that the air inside the cleanrooms is virtually free of contaminants. The second pillar is maintaining appropriate environmental conditions. This includes controlling temperature and humidity to provide stable conditions for both the product and the operator. Proper pressure cascades are also critical to prevent contaminants from entering the cleanrooms from outside. The third element is the construction and finishing of surface. All surfaces must be smooth, easy to clean, and resistant to particle accumulation to minimize contamination risk. The final pillar is operational procedures and gowning. Operators must wear special clothing that limit particle emissions from the body and follow strict hygiene and disinfection protocols. So, what are the applications when we use the cleanrooms? Cleanrooms play a fundamental role in three key areas. In pharmaceutical industry, they ensure sterile conditions for drug manufacturing and packaging, which is essential for patient safety and effective contamination control. In semiconductor production, their importance is even more critical, because just a single speck of dust or microscopic fiber can cause a short circuit, a defect in the silicon structure, or a complete microchip failure. This can lead to massive financial losses and production delays, which is why cleanliness control here operate at the nanometer level. In biotechnology and medical device manufacturing, cleanrooms support processes such as cell culture, genetic engineering, and sterile assembly of implants and surgical instruments, where every component must meet the highest aseptic standards. So, how do we standardize the level of air cleanliness in the room? This question is answered by the standards mentioned earlier, GMP and ISO. In this presentation, I would like to focus on the GMP standard because it primarily applies to the cleanrooms used in pharmaceutical manufacturing and is the most commonly implemented in this field. The table shown here defines cleanrooms classes based on the number of particles and the state of the room. There are two states: at risk, where equipment is installed and operating, but no personnel are present, and in operation, equipment is running and production processes are taking place with operation present. The permissionable particle count in the air varies depending on the state. The GMP standards define four main cleanroom classes: A, B, C, and D. Class A represents the cleanless environment where particle concentration must remain extremely low in both states. Additionally, laminar airflow is required. On the other hand, Class D allows a much higher particle count, but still under strict limits. For example, in the at-risk state, the maximum is 3,520,000 particles larger than half microns and 29,000 particles larger than 5 microns per cubic meter. For comparison, a typical office room contains more than 300 million particles larger than half microns per cubic meters. That illustrates the enormous difference and how demanding cleanroom standards truly are. Since we now know what cleanrooms are, what requirements they must meet, and how air cleanliness and particle levels are classified, we need to answer one more question: who or what ensures these conditions are maintained and prevents contamination? The answer is simple. A properly functioning ventilation system plays the key role. It reduces the amount of airborne particles, maintains critical environmental parameters such as temperature, humidity, and pressure, and, as mentioned earlier, protects the room from the ingress of airborne contaminants from outside. Let's move on the limitation we face when implementing sustainable ventilation in cleanrooms. First, air quality requirements. Cleanrooms operate under strict ISO 14644 and GMP standards. These standards mandate compliance with particle concentration limit, pressure differential, and validated airflow patterns. While they do not impose fixed air change rate, they require proven contamination control and recovery times. This makes reducing airflow challenging without extensive risk assessment and validation, limiting straightforward energy optimization. The next challenge is system flexibility. Traditional HVAC installations are typically designed for constrained air volume (CIV) operation. They lack advanced controls such as VIV, variable air volume, or real-time particle monitoring, which would allow dynamic adjustment of airflow based on actual contamination levels. Finally, investment cost implementing energy-efficient solutions required advanced sensors, automation systems, and additional ventilation processes. These upgrades involve significant capital expenditure, and without a clear return on investment, it can be difficult to justify this cost to stakeholders. Now that we understand the importance of proper ventilation, the requirements it must meet, and the challenges it faces, the question arises: how do we design and implement a system that fulfills all these expectations? A system that ensures the right level of air purification while remaining aligned with sustainable principles. One answer to this question is the emission-based modeling approach. This is a specific method for designing and implementing ventilation systems that focus on optimization based on actual source of contamination within cleanrooms. How does it work? First, we identify the source of contaminant emissions. Next, we calculate the airflow required to remove them. The following step is to design a mechanical ventilation system capable of adapting to changing conditions, and emission source during the room's operation. Finally, we design and implement an intelligent control system that manages the entire process, ensuring the system is both energy efficient and safe. Following our approach, historical data shows that the main source of contamination in cleanrooms vary. The largest contributors is personnel, responsible for up to 80% of total emissions. This includes shading skin particles, hair, breathing, and fibers from clothing. Other sources have a much smaller impact. For example, equipment and tools about 5 to 10%, air system and HVAC also between 5 to 10, materials and packaging around 5, and facility surfaces less than 5%. This structure clearly shows that by knowing the number of people present in the room, we can estimate the amount of contaminants generated. In turn, this allows us to dynamically adjust ventilation system parameters, maintaining environmental cleanliness while optimizing energy consumption without compromising process quality. From the previous slides, we know that personnel are the main source of contamination in cleanrooms. This insight is crucial when designing the ventilation systems. Traditionally, systems are designed based on fixed air change rates. For example, grade D, ISO 8, typically is 10 to 20 air change per hour. For grade C, ISO 7 is between 20 to 40 air change rate per hour. And for grade B, ISO 5 at risk stage, as high as 40 to 60 air change per hour. The problem is that this approach does not account for actual particle emissions, which depend primarily on the number of people in the room. That's why a new trend is emerging: emission-based modeling. In this approach, we define a target recovery time, for example, 10 to 20 minutes, to reach the at-risk state and design the system based on real emission source. This enables more precise and energy-efficient solution without compromising environmental quality. Let's now look at how airflow volumes differ in practice depending on the calculation method. As an example, we have a room with area of 50 square meters and height of 5 meters, classified as grade C, ISO 7, with five people present. First method based on air change per hour, with 20 to 40 air change per hour, we get between 5,000 and 10,000 cubic meter per hour. This is a very high volume, typically of the traditional approach. Second method, based on recovery time, for a target of 15 minutes, the result is about 3,290 cubic meter per hour, significantly lower than the air change rate method. The third method, based on emission modeling, with 5 operators, the airflow is approximately 1,720 cubic meter per hour. This is the most energy efficient solution because it is tailored to the actual source of contamination. It is important to note that for the second and third method, the system must still be sized for a higher airflow to meet recovery requirements. However, under normal operating conditions, it can run at a capacity close to the calculated using the third method. A ventilation system based on the recovery time and occupancy-driven control must be far more advanced than traditional CIV solutions. Key components of such a system include variable speed fans, enable smooth regulation of airflow across a wide range, VIV dampers on supply and return, allow dynamic adjustment of airflows to current requirements, both during normal operation and in recovery mode. Advanced control automation integrates flow regulation algorithms based on processes parameters and load scenarios. Occupancy sensors enabled automatic switching between operating mode and energy-saving mode when the room is empty. Unlike the traditional approach where the system operates at the fixed point, this solution offers full flexibility, high airflow for rapid recovery, and reduced airflow during low load periods. The result is significant energy savings. Now that we covered the mechanical part, I'll hand over to Damian, who will tell us more about the cleanroom control system design.
Thank you, Roman, and welcome everyone. We have seen how air gets in and out. Now let's talk about how it knows who is in the room and whether it should even bother showing up. Cleanroom control systems are divided into three key components. The building management system, BMS, in this case is the key control system for the mechanical HVAC equipment discussed earlier. It is the BMS that ensures proper conditions in the cleanroom, and through appropriate control, it does so in an optimal manner. An environmental monitoring system, EMS, also known as validated BMS, is essential in cleanrooms to ensure continuous control over critical parameters such as airborne particles, temperature, humidity, and differential pressure. Regulatory frameworks like EU GMP Annex 1 and ISO 14644 emphasize the need for real-time monitoring to maintain compliance and product integrity. EMS also supports data integrity requirements outlined in 21 CFR Part 11, enabling traceable, validated, and secure environmental data management. The Access Control System, ACS, is crucial in cleanroom environments to ensure that only authorized personnel can enter controlled areas. It helps maintain contamination control by regulating access through personal airlocks, PAL, and material airlocks, MAL, which serves as buffer zones between clean and non-clean areas. By integrating ACS with other cleanroom systems, the system supports traceability and reinforces compliance with operational hygiene standards. Nowadays, the building management system is becoming just as important as the main process control system. The range of subsystems integrated by BMS often makes it the most extensive system within the facility. In this case, however, we focus on its narrower function, controlling HVAC systems. The HVAC BMS plays a central role in maintaining cleanroom conditions. It controls airflow volume and air changes per hour, ensuring that the cleanroom meets its classification requirements. It also manages pressure cascades between zones to prevent cross-contamination. Temperature and humidity are regulated to maintain comfort and process stability. According to our concept, we also want the BMS to optimize the operation of the installation based on demand resulting from changes in the number of people present in the room. This responsiveness is essential for emission-based modeling, where airflow is tailored to real-time contamination risk. By leveraging smart controls, the BMS supports both energy savings and regulatory compliance. The Environmental Monitoring System, EMS, is a validated component of the BMS architecture, or alternatively part of a process DCS system. It continuously monitors and records key environmental parameters such as differential pressure, temperature, humidity, and optionally particle concentration. All records are securely archived to ensure traceability and audit readiness. The requirements for monitored parameters, including target values as well as guidelines for warning and alarms, are defined in the User Requirement Specification URS. This ensures that the EMS operates in full alignment with the expected environmental conditions and compliance standards. The Access Control System, ACS, serves multiple functions in cleanroom environments. It regulates personal access to sensitive areas, preventing unauthorized entry and reducing contamination risk. ACS also supports occupancy monitoring, which is crucial for dynamic ventilation control. By tracking who enters and exits the cleanroom, the system enables real-time adjustments to airflow. Additionally, ACS contributes to audit and compliance efforts by maintaining access logs and integrating with environmental systems. Its role is in contamination prevention, and data collection makes it a vital component of emission-based modeling strategies. Now, let's take a look how these systems work together to achieve what we call emission-driven cleanroom ventilation. As I mentioned earlier, there are three key players here: the BMS, the ACS, and the EMS. The EMS, Environmental Monitoring System, keeps an eye on the pressure cascade between the cleanroom and the adjacent personal airlock, which is PAL. It uses its own dedicated differential pressure sensor, and if something goes wrong, it raises an alarm. The BMS, Building Management System, plays the main role in maintaining proper conditions. It also monitors the pressure cascade using its own sensor and collects information from the ACS about how many people are inside the room. Based on that, it controls two VAV boxes to adjust ventilation according to occupancy while keeping the pressure cascade stable. It can also trigger alarms if needed. Finally, the ACS, Access Control System, does more than just manages who can enter the room. It also tells the BMS how many people are inside. Together, these systems create a smart, integrated approach to cleanroom ventilation. Cleanroom ventilation operates in three distinct modes: in operation, recovery, and at rest. During operation, airflow is adjusted dynamically based on the number of people in the room. This ensures that contamination risks are managed in real time. In recovery mode, airflow is increased to restore at rest cleanliness within a target time. Once recovery is achieved, the system switches to at rest mode, where airflow is minimized. These modes allow for efficient energy use while maintaining cleanroom standards. Emission-based modeling leverages these modes to optimize ventilation based on actual contamination risk and occupancy patterns. Accurate occupancy monitoring is essential for emission-based ventilation control. Integration between the BMS and ACS allows for tracking the flow of personnel into and out of cleanroom zones. However, challenges such as tailgating, where individual bypass access controls and hardware malfunctions can compromise data accuracy. To address this, redundant monitoring methods can be employed. Anti-tailgating sensors detect unauthorized entries, while real-time occupancy counters using infrared or camera-based systems provide continuous tracking. These technologies ensures reliable occupancy data, enabling smarter ventilation control and maintaining cleanroom integrity under dynamic conditions. Roman, back over to you.
Thank you, Damian. Now let's review the assumptions and analysis scenarios. The cleanroom under analysis is grade C with an area of 50 square meters, a height of 5 meters, and an expected occupancy of 5 people. As a reference point, we use the standard air change method, 30 air change per hour. Importantly, in this scenario, we assumed continuous ventilation operating and this rate and airflow 24 hours by 7 days a week. Additionally, in the emission-based model, we defined 3 operating modes: 16 hours of operational work, 1 hour in a recovery mode, 7 hours at rest. And based on this assumption, we carried out an analysis of both operating and investment costs. Our solution delivered results that exceeds expectation. Investment costs were reduced by 30% and operating costs by almost 80%. How did we achieve this? We minimized the size of installation, which lowered expenses for ducts, fittings, and accessories. We reduced the number of HEPA filters and downsizing the main ventilation unit, the biggest cost driver. Although we had to increase spending on automation and control system, the overall balance remained strongly positive. Why does it work? Less airflow means lower energy consumption. Fewer devices and filters result in a lower maintenance and service cost. The outcome? The installation is cheaper from the start and in operation brings significant savings throughout its life cycle. This approach is worth implementing in future projects. Thank you very much for your attention. And now I hand over to David.
All right. Thank you very much, Roman, Damian, and Paul, for a very informative webinar. We're going to now take a moment to address a few questions that we've received from the audience. And again, as a reminder to those attendees on the call, please make use of the Q&A tab to ask any questions, which is situated at the top of the panel. So the first question that I'd like to get answered, I'm going to address with Roman. And the question is this, Roman. In pharmaceutical clean room environments, how do the differences between ISO 14644 and EU GMP standards impact the design, particularly when facilities must comply with both sets of requirements? Could you share a bit of context on that with us, Roman, please?
Sure. Thank you for this great question. Before I answer directly, let me explain the main differences between the two standards. ISO 14644 is an international standard for classifying clean rooms in any industry. So in electronics, semiconductors, or pharmaceuticals. EU GMP Annex 1 is a guideline specifically for the manufacture of sterile medical products. So it is focused on pharmaceutical design. The key differences are in particle size monitoring, microbiological control, and operating states. Regarding particle size monitoring, ISO standards consider particle ranging from 0.1 microns to 5 microns, where EU GMP Annex 1 focus specifically on particles larger than half microns and 5 microns. In terms of microbiological control, Annex 1 required active monitoring for microorganisms, which is not addressed by ISO standards. Regarding operational states, ISO does not differentiate between at risk and in operation conditions, while Annex 1 clearly distinguishes between them. For example, a Grade B cleanroom must meet ISO 5 requirements when in at-risk mode, but only is ISO 7 during operation. When we're designing our facility, we focus on the more strict requirements, and that is usually Annex 1.
All right. Very well, Roman. Thanks very much for a detailed reply to that question. The next question I'm going to send over to Damian here, and it's a two-part question. The first part is this: what are the limitations of current HVAC systems in supporting real-time emission-based control? And the second part is, may they be retrofitted? So I'll give you a chance to reply to that, Damian.
Thank you, David, for that question. And to be honest, I don't really think existing HVAC systems have limitations that would stop upgrades. I mean, this kind of upgrades, they are already happening, and we are actually helping with them. Sometimes it's just updating the BMS PLC software, which is not too expensive. Other times, you need to add some extra sensors or control devices, like VAV units, for example, and that, of course, means a bigger investment. Also, PLC controllers that are part of the BMS, they can be installed locally, just for a specific area. So it is possible to modify the system step by step without, changing everything at once. Then there's, of course, an integration part. Of course, we need to think about it, but today controllers are quite flexible. They support different interfaces, so it is possible to interface with the main control system, which is already there. And there are also other solutions, other products which can help with such integration too. So it is possible to upgrade those installations, and to be honest, these days I don't see limitations for those systems preventing to do such upgrades.
All right. Appreciate your reply to that. We have another question here that speaks to actually practical implications, and I'm going to ask Roman to address this. Roman, what are the practical implications of Annex 1's emphasis on contamination control strategy compared to ISO's particle count classification? Thoughts on that?
Okay, that's also really good questions. So Annex 1 goes beyond practical counting and introduce a holistic contamination control strategy. This means that both design and operation must address all potential contamination sources: particles, microorganisms, personnel, equipment, and material flow. ISO 14644 focuses mainly on airborne particle contamination, which is important, but it's only one part of the overall contamination risk. In practical terms, this means that a fully integrated design approach is essential. HVAC system, pressure cascades, airlock, and material transfer zones must be carefully planned, and not only to meet particle count limits, but more implementally to minimize contamination risk. Annex 1 also place strong emphasis on controlling the flow of personnel and materials, requiring strict segregation and clearly defined pathways to prevent cross-contamination. Future more environmental monitoring under Annex 1 goes beyond particles counts. It mandates continuous surveillance for viable organisms and risk-based sampling strategies. Finally, the concept of life cycle thinking is central to the contamination control strategies, which demands documented risk assessment, validated cleaning procedures, and ongoing reviews. This level of process integration is not required by ISO standard. So, long story short, Annex 1 drives a risk-based comprehensive contamination control philosophy, while ISO provides a technical framework for particle cleanliness. For projects that must comply with both, Annex 1 usually dictates the design strategy because it's stricter and processes orientated.
Very good, Roman. We have a question. I'm going to stick with you, Roman, on this one as well. We have a question here from our audience member. Some clean rooms have gas, vapor, or powder sources that result in electrical hazardous area classification. How does this impact the design? Is the question, Roman.
So yeah, that is also a really good question, because we have some powder sources. Sometimes we have the explosive zones. We need to provide the special fume hoods from that, or special laminar flows, which are designed in this area to protect operators and also protect the rooms before releasing of this product. So this is one of the things which we need to consider. Additionally, when we have this kind of materials in clean rooms, so we need to think about exact equipment which we use, because that it also needs to be designed in explosive proof type. Yeah, we also need additional snorkeling or exhaust laces where the contamination is generated. So it's a really complex design in these cases, and that required a very deep analysis. What materials are used, where they are located, how they will be used by the operators, and based on this certain information, we can design exact our ventilation system.
Okay, very well. There's one more question I'm seeing here from the audience members, Roman. I'm going to stick with you again, and it talks about air turnover rate. I know in the presentation we talked a lot about air turnover rates for clean room spaces, but the question in this case is, for comparison's sake, what is a typical air turnover rate, or I think as we referred to it, an ACH in the presentation, for a typical non-clean room space? So can you comment to that, please?
Sure. This question is also very good, because the answer isn't simple, because it really depends on what the ventilation is for and what its purpose is. The required air change rate will be different in a production area, or in the office, or in a warehouse. If ventilation is used to remove harmful substances from processes, the airflow will need to be much higher. If the goal is to provide thermal comfort, the rate will be moderate, I can say. And if it's only about supplying a minimal amount of fresh air for sanitary reason, the airflow will be the lowest. So there are many factors that influence the air turnover rate. In typically non-cleanroom spaces, it is much lower than in clean rooms. Usually it doesn't exceed 6 air change per hour. And in many cases, it's even lower, around 1 to 2 air change per hour.
Okay, great. Thank you very much, Roman, for that reply. I just saw one final question pop in here, and I think we're going to have time to address it quickly, given the time we have remaining. With efficiency and cost in mind, and I'm going to offer this to either Damian or Roman, either of you can jump in and reply to this one. With efficiency and cost in mind, do you recommend independent HVAC systems for clean room suites, or as part of a composition of multiple clean room suites in a common system? So I think the question is really focused on an independent system versus a system that would service multiple clean room suites. So could either one of you, or maybe even both, comment to that briefly, please?
Okay, so maybe I start with that. The answer on this question is difficult, because when we're designing the air handling unit system for the clean rooms, we not focus on the efficiency. We need to know what is produced, what is used in the suites. If the suites are using for the same purpose, the product is the same, maybe it's efficient from the cost perspective, only investment cost perspective, to design only one air handling unit system. If it's if the system will be not too big to serve those 2 or more suites. However, if the different substances are used there, and it is a risk of cross contamination, then probably single system should be designed for each suite. Yeah. Additional values which needs to be considered are the distances between the suites and the size of the factory, location of the machinery room. Yeah, there are many aspects which needs to be considered when we designing the system. So the answer is not really simple.
All right, Damian, is there something else you may like to add to that?
From the control system point of view, generally the control system must serve for the mechanical installation. So if the mechanical system is divided into few groups, then our also should be. I don't see any reason to separate the BMS system only for serving clean rooms. It can be part of the whole BMS system. We need to remember that BMS system, I mean the second level, I mean controllers. Controllers can be installed locally, so the controller still serves only for the clean room, but is a part of the whole BMS. So from control system point of view, really it doesn't matter. We still need to control the mechanical devices, and this is the main point where we need to follow the installation.
Okay, wonderful. Thank you very much for that, Damian. I'm not seeing any more questions coming in from the audience, and I see we're nearing the top of the hour here. So with that, I'd like to thank you again, both Roman and Damian, for what I'd call a very informative webinar on this subject, and certainly the time that you have spent both today and in preparation for today's event. Also, thank you so much to our audience for attending today. It certainly has been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on Fluor.com or following our social media channels using hashtag Innovation Builders. If you'd like us to send you an email notification of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention and thank you again for dialing in today. We will send out a compiled list of the Q&A shortly, along with the notification that the webinar recording is available for replay on Fluor.com. If you have any questions or require additional information, please email innovationbuilders@fluor.com and someone from our team will get back to you. From all of us at the Innovation Builders team, have a great day and thank you.